I'm going to speak for a few minutes just on basic steel making. And steel making is a very important process, as you all know. It's the foundation of sort of modern civilization, if you believe in building buildings and making other things that require real strength. And it's also a pretty big CO2 emitter. And as you'll hear in a few minutes, it's a little bit of a conundrum to figure out how we're going to make steel without emitting quite a bit of CO2. So what I thought I would do, because probably most people haven't trolled around steel plants like I have, in big, which can be as big as 25 or 30 square miles. That's how big an integrated steel mill is. And they move millions of tons of material a year. And so I'm going to talk a little bit about the basic processes and just kind of set the stage for what's what. And then Paul's going to take over and talk about some of the efficiencies that are being brought to bear now, some of the things you could imagine in the future, and then I think probably still leave us with a bit of a conundrum about what we're going to do and why this is such an important area of research and work that needs to happen. So in basic steel making, nobody will be able to read my handwriting, so I'll just tell you what's up here. There's iron 3+, iron oxide, using carbon monoxide in a blast furnace to reduce it to iron 0, and then you take it on to make iron alloys from there in the basic oxygen furnace and other processes. And that's 70% of the world's steel is made that way. There is also some steel or iron that is made from magnetite, iron 2+, and kind of ironically, and I've worked at some of these plants, you take iron 2+ to iron 3+, putting a lot of energy in, even though it's an exothermic process, and then you take the iron 3+ and you bring it back to iron 0. And really what they're doing there is they're taking iron 2+ magnetite, which is typically in a powder form and not structurally strong, and they turn it into an iron pellet that you can then stuff into a blast furnace, and it can support the weight of hundreds of tons of material. So I worked with a company that actually, we came up with an approach, because this is an exothermic process going from iron 2 to iron 3, oxidation, that they could actually produce all that iron 3 and have enough excess energy to run an electricity generator to power the whole plant. So that in principle is possible, but there's not very much of this process going on in the world. But those are the two basic things that go on for iron making, and that's called virgin iron. It starts from raw materials. There's also electric arc furnace. For those of you who've heard of Nucor here in the United States, it's a big mini mill company. It actually has taken a large amount of market share in the last 30 years from the integrated steel folks. And there you really take iron alloys and you turn them into new iron alloys by melting them in an electric arc furnace and adding pixie dust and a few other things to come up with some pretty high quality steel. And Nucor is continually making better steel, but they still can't make the quality steel you get from virgin iron. And so it doesn't go into, say, Class A body panels for cars. And so that's actually something to think about. Is there a substitution play here at some point? Because steel's real strength is in its strength, not in its beauty. And then finally, there's DRI, direct reduction of iron. It uses actually methane, and you can produce a partially reduced iron pellet, which then is fed into blast furnaces. So that's kind of what goes on in iron making. To talk a little bit more about the blast furnace system, and actually some numbers over here. So blast furnace, it's roughly 2 tons of CO2 per ton of steel out. EAF is about 0.5 to 1.5, depending on the electricity source. And there you can imagine doing it all with renewables.
But not the top. You need direct CO2
No,
as the
right,
product.
not the top.
You didn't write that.
No, I did not. Well, it's CO2, and CO2 comes out. Yeah.
CO2 comes out.
Yeah. Lots of it, in fact.
Can you say where the carbon monoxide is coming from typically?
It's coming actually from the coking coal in the blast furnace. So there's a complex set of reactions that go in the mid-level of a blast furnace that are creating CO, which is reducing it.
And is that included in the 2 tons? Because you have some CO2 emissions associated with that too, the coal conversion.
Yeah, let me talk about that in a little bit more detail. But yeah, there's a lot of stuff going on there. So and then finally, DRI is about 0.7 to 1 ton per ton. So, I mean, there's significant amounts coming out. Now, in a blast furnace, the basic process is you've got to make the material. So you take coking coal, you drive off all the volatiles right there. You used energy to drive them off. And you also created a gas that's highly valuable in energy. You typically take it somewhere else in the blast furnace and you combust it and you make CO2. You have to make sinter. That's taking iron ore fines, melting them together into an agglomerated lump that can hold some mass, some weight support, and that takes energy. And then you also make these iron pellets that you sprinkle in there as well to support. So those are all endothermic processes that typically then create quite a bit of CO2. In the blast furnace, you have this stack of material. The primary one that's producing CO2 is the coking coal that's in there. And through a complex set of processes, it creates pig iron, but it also, the gas that's then emitted has CO in it, which you actually use, either you recycle it, which Paul will talk a little bit about, or you move it to other parts of the plant and you burn it, and you turn it into CO2, but ultimately it turns into CO2. And then in the basic oxygen furnace, you're taking the pig iron, you're adding scrap metal to it, you're adding oxygen to it to burn off the remaining carbon that's in the pig iron and the steel to give you the kind of alloy and strength that you want. So that it also emits CO2 and quite a bit of heat. And then finally, you continuous cast that pig iron, but you typically let it cool down to something that's well below glowing red temperatures. You have to heat it back up and then roll it through rollers. And so that itself takes quite a bit of iron, because you take it from maybe either room temperature up to a couple hundred Fahrenheit up to annealing temperatures. And so you use quite a bit of energy in there. And the breakdown is roughly this. You know, the power that you actually produce in the plant from these different gases is around 700 kilograms of that 2,000. 330 is in the blast, 290 in the sinter, and 285 in the coke. And the rest is in everything else. And that's roughly the breakdown of the energy in the blast furnace.
Great. So is that energy or CO2?
These are all CO2, ton,
Sorry, that's CO2.
kilograms per ton.
Kilograms CO2.
Kilograms per ton, yeah.
Right.
So,